Hi everyone. So in this video, we're going to be talking about our last type of transformation, which is stretching and compressing graphs. I just wanted to quickly remind you what the other types of transformations are that we talked about, just to kind of contrast them. So remember that we first talked about shifting a graph. And so what we saw is that a shift occurs in your graph. So taking that graph and moving it, that occurs when you add or subtract a number either to the function itself or to the input of the function. So this is something we'll review in the next video, but just to remind you, adding or subtracting, that corresponds to shifting your function. And then we saw that in our last video, we saw that if you negate, meaning if you add a negative sign, multiply by -1, either to the function as a whole or to the input of the function, that gives you a reflection. And so what we'll be looking at today is taking a function. So if you look over here, taking a function and multiplying it by a number, right? We haven't talked about that yet. I mean, reflections are really multiplying by -1, but we haven't looked at what happens if you take a function and multiply it by 2. And then we'll also see what happens if instead of taking the whole function, you take the input of the function and multiply it by a number. And so what we'll see is that these give us stretches or compressions in our graph. Okay, so we're going to use the same example, same kind of structure that we've been doing, where we'll start with one concrete example so that we can really see why the transformation works the way it does. And then once we've done that, we'll establish what the rule is. And then once we have the rule in hand, we can go and do some more examples. So again, we're just going to fill out this table for the square root of x. That's going to be our kind of basic starting graph. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So same graph that we were working with in the last video in our first few examples. So here are some points on the graph, and that is what our square root graph looks like. Okay, so the first transformation we're going to be looking at is taking the function f of x and multiplying it by 2. So just as we've been doing, we want to start by rewriting the function g of x so that we're not writing it in terms of f of x anymore. So 2 times f of x just means that we're going to take whatever our function is, our function f of x, and multiply it by 2. So what's that going to look like? Well, it's going to be 2 times the square root of x. And so how is this going to affect our outputs? Well, as we plug in these numbers, we're still going to take the square root of them, but then we're just going to multiply the result by 2. And you can even kind of see that without actually writing this formula out, because what we're doing is we're evaluating f of x. That was the outputs of the original function, and then we're multiplying those results by 2. So if we take the square root of 0, that's 0, multiplied by 2, that's still 0. Square root of 1 multiplied by 2 is 2. Square root of 4 is 2, multiplied by 2 is 4. And then finally we have square root of 9 is 3, multiply that by 2 and we get 6. So now we can plot these new points. So we still have 0, 0. Now we have 1, 2. Now we have 4, 4. And then we have 9, 6. Okay, so how would you describe how this graph has changed? We can tell that it's like higher up, but has this graph been like shifted or what's going on here? So this graph has not been shifted. How can we tell that this is not a vertical shift? Well, with a vertical shift, every point in the graph would be moving the same number of units up, right? If you have a vertical shift, it's like, oh, shift the entire graph up by 1. And if you look at how far these points have gone, well, the point at 0, 0 actually stayed right where it was. This point only moved up by 1. This point moved up by 2. This point moved up by 3. So it's not a shift. And then additionally, whenever you have a shift, the shape of your graph should stay exactly the same. And this one, the shape kind of changed, right? It got steeper at the beginning, the whole graph basically got steeper. And so what this actually is a vertical stretch. And specifically, it's a vertical stretch by a factor of 2. And so what do I mean when I say by a factor of 2 or by 2? I mean that we multiplied all of the y values by 2. And again, that really makes sense because that's exactly what our function was, right? Our function is taking our original function and multiplying it by 2. So of course, all of the outputs are getting multiplied by 2. And in the graph, that looks like all of the y values getting multiplied by 2. So stretching your graph vertically by 2 is going to look like this. And it's going to, again, be, to specifically graph it, you're just multiplying all of your y coordinates by 2. Okay, so now we have our multiplying the input by 2 instead of multiplying the function by 2. So we'll see how that plays out differently. So I'm just going to start by sketching our original function here. Okay. So our function in this case is, instead of it being 2 times f of x, it's f of 2x. And so we need to figure out how to rewrite that in as kind of a standard formula. So remember that anytime you're evaluating a function and you're plugging in an expression, you're basically just replacing x with that expression. So since our original function is f of x is equal to square root of x, if we're plugging in 2x instead, well, that just means we're doing square root of 2x. And that's different from 2 times square root of x. And we'll see that it's different when we go and actually plug in points. So basically, as we've seen in some other examples, there's a distinction between, are you multiplying the entire function by a number, or are you multiplying the input by a number? Okay, so let's go and fill out this table. And at first, this table might seem a little funny, like the values I put, but I think once we do a few of them, you'll see why I picked the values I did. So I'm actually going to write these out just to really let us see where they're coming from. So how would we evaluate h of 0? Well, we would be doing the square root of 2 times 0. 2 times 0 is still 0, and the square root of 0 is 0. So that point is still going to be 0, 0. What about h of 1/2? Well, then we'll be doing the square root of 2 times 1/2. And so what is 2 times 1/2? Well, it's 1, right? And so we have the square root of 1, which is 1. Next up, we have h of 2, which is going to be the square root of 2 times 2. And so that's the square root of 4, which we know is 2. And then last we have h of 9 over 2, which is going to be the square root of 2 times 9 over 2, which is the square root of 9, and we know that the square root of 9 is 3. Okay, so let's go ahead and plot these points. I'm just going to erase this to make space for later stuff. Okay, so our points are going to be, we still have 0, 0. Now we have 1/2, 1. Then we have 2, 2. And then we have 9 halves. So 9 halves is 4.5. 9 halves, 3. So that's here. And so our graph looks like this. And so again, in this case, you might look at this and say it looks like it's been stretched vertically. And that actually, that is correct. It has been stretched vertically. But basically, a lot of the functions that we are looking at in this class, you can either see changes to the graph as a horizontal stretch or compression or a vertical stretch or compression. It's just kind of a point of view thing. I want to focus on this. I want to focus on thinking about what happened horizontally rather than vertically. And then later on in the video, we'll see some examples where there is a more clear distinction between what's horizontal and vertical. But focusing on what happened to the x value. So try not to think of this as being stretched upward, but think about what was happening horizontally. If we were to kind of pull or push this graph horizontally, is it getting squeezed to be narrower, or is it getting pulled out to get wider, right? Because if it's getting stretched horizontally, that would mean that it's getting kind of wider and flatter. And in this case, it's actually doing the opposite, right? It's getting compressed. Like picture if you kind of push your hand against this original function in black, it would kind of smush inward to look like the purple one, right? And so that's what I mean when I say it's a compression. It's been compressed. And so how much has this been compressed by? So I'm going to say it's been compressed horizontally. Well, if you compare, if you kind of look at like what, so, in this example, we said it was stretched vertically by 2 because all of the y coordinates were doubled, right? We had, instead of 1, 1, it went to 1, 2. Instead of 4, 2, it went to 4, 4. Everything, all the y coordinates were doubled. And so similarly, if we're trying to figure out how to describe this horizontal compression, we can see how do the x coordinates compare. And so if we look at the x coordinates that are at the same height, for example, these two, the original function has an x coordinate of 1, and the new function has an x coordinate of 1/2, right? Looking at this point and this point. And then our next point has a y coordinate of 2. The original function has an x coordinate of 4, so that would be this point. And the new function has an x coordinate of 2, so that's this point here. And then the third point on the graph, so the original point had an x coordinate of 9 and a y coordinate of 3. The new point has an x coordinate of 9/2 and a y coordinate of 3. And so what's going on here is that all of the x coordinates are getting multiplied by 1/2. Right? If you compare, just like looking from one table to the next, the y coordinates are all the same. The x coordinates are all half of what they were in the original function. Okay, so why would that happen? That's kind of backwards, right? If you had to guess what was going to happen to this, I mean, I personally probably would have guessed that this was going to get stretched horizontally by 2. Right? Because we saw that when you multiplied f of x by 2, it stretched it vertically by 2. So why doesn't it, when we're multiplying the input by 2, why doesn't it stretch horizontally by 2? Well, the reason is basically the same as the reason for why, remember when we talked about horizontal shifts, those go kind of backwards of what you would expect, right? If you add a number, it's going to shift to the left. If you subtract a number, it's going to shift to the right. And it's really the same idea. It's because it's kind of this idea of compensation, right? Like because we're multiplying the input by 2, that allows you to plug in a smaller x value and achieve the same height, right? So for example, in the original function, in order to achieve a height of 3, you have to plug in 9. And so that would be this point here. In the new function, you don't have to plug in 9 anymore to get to a height of 3. You only have to plug in 9/2. And so why is that? It's because you're multiplying by 2 inside the function. So that extra factor of 2 is kind of allowing you to plug in smaller x values in order to achieve the same y value. And so that has the effect of compressing the graph horizontally because you're plugging in smaller x values and getting the same y value. And so basically the x coordinates are sliding inward while the y coordinates are staying the same. And that is going to have the effect of compressing the graph. I think this is probably one of the hardest things to understand why it works. So if you're a little confused still by this, like every time I teach this, I feel like I spend a lot of time explaining it, and then I still have students coming up and asking me about it. So I know it's a hard thing to grasp. So it's one of those things that I would really recommend sitting down, maybe do another example for yourself, compare the tables side by side, really try to convince yourself of why it's working out the way it is. Okay, so now that we've seen some of these examples, let's try to Okay, so now we're going to summarize what we've seen in these two examples in a table like we did with the others, and then we'll go and look at some further examples. So the first one that we did, what was the change that we made to our formula? Well, we were multiplying the function by some number c. And so what did we see happened in the first example? Well, in our first example, we multiplied the function by 2, and what happened was that the graph did a vertical stretch. By a factor of c. Right? So in our example that we already did, c was 2, so the graph stretched by 2. Now there's something that we didn't see yet, which is that basically whether the graph is going to stretch or compress vertically is going to depend on the value of c. So with vertical stretches, they kind of play out exactly the way you would expect. So whichever number you're multiplying your function by, the graph is going to, all the y coordinates will be multiplied by that number. So for example, when we did 2 times f of x, that made the graph 2 times taller. But what if instead we did, let's say, 1/4 times f of x? What do you think that would do? So if we did 1/4 times f of x, that wouldn't stretch the graph, right? It would compress it down vertically. So what I'm going to finish writing here is that it's a vertical stretch by c if that number c is bigger than 1. So if you multiply your function by 2 or 3 or 1.1 or any number that's bigger than 1, that's going to have the effect of making the y coordinates higher numbers, which will stretch the graph vertically. What will happen if we multiply by a number smaller than 1? Well, that will then be a vertical compression. If c is less than 1. So how would you actually do these in the graph? Well, basically in either case, so I'll put it kind of in the middle, in either case, you're just multiplying all y coordinates by whatever that number is, by c. So again, if it's 2, like what we just did, everything gets twice as tall. If it's 1/4, well then every point is going to become 1/4 of its original height, so it'll get smushed downward. Now, on the other hand, when you're doing a horizontal stretch or compression, that's where things get a little confusing. That's where they don't work exactly the way you would expect. So what we saw is that, so what number were we working with? We were working with 2, right? The example we did was f of 2x. And so what happened is that we actually got a horizontal compression. And what was our horizontal compression by? Well, it was actually by 1/2. And so I'm going to write that in general as 1/c, if c is greater than 1. So basically what's going on here is that, again, for vertical stretches and compressions, they work exactly like you would expect. Whatever that number c is going to tell you exactly what's happening to your y coordinates, which will tell you exactly how much the graph is going to stretch or compress by. The key thing to understand for horizontal compressions and stretches is that you're always going to take the reciprocal of whatever number you're multiplying x by. So in our example that we already did, we had f of 2x, and so that became compressed by 1/2. If we had f of 3x, it would become compressed by 1/3. If we had f of 5x, it would be compressed by 1/5. So you're always taking the reciprocal of whatever number you're multiplying x with. So what happens if the number you're multiplying x with is itself less than 1? So like, let's say that you did f of 1/2 x. Well, that's actually going to stretch your graph. So they basically just kind of work backwards. So it's going to be a horizontal stretch by 1/c if c is less than 1. And I know this probably feels like a lot of different rules. Don't worry, we're going to do some examples that I think will make this a little clearer. But again, the most important thing to know is that for vertical stretches and compressions, you're multiplying the y coordinates by whatever this number is. Whereas with horizontal stretches and compressions, you're now multiplying the x coordinates by the reciprocal of that number. And we talked about why that is. It's basically this idea of compensating. It has to do with what numbers you can plug into the function to achieve the same height. And so how do you actually graph this? Well, you multiply now all x coordinates, not by c, but by 1/c. So it's always the reciprocal with horizontal stretches and compressions. Okay, so let's look at some examples. All right, so first example I want to do, we are going to use transformations to graph g of x is equal to 1/3 times the absolute value of x. So let's start by figuring out what is the kind of basic function that we are transforming here. Well, in this case, it would be f of x is equal to absolute value of x. And so let's start by sketching that graph. I'm going to plot a few points. You don't really need to plot that many points for absolute value graphs because it's a straight line. If once you have a couple, you can just connect them, or because each half, I should say, is a straight line. But I'll just do a good few for good measure. Okay, so that's our original function, the absolute value of x. All right, so now we need to figure out what is the transformation here. So we're multiplying by 1/3, and we're multiplying by 1/3 on the outside of the function. And so what does it mean when we multiply on the outside of the function? That means it's going to be a vertical stretch or compression. So this is something we'll talk more about in the next video when we kind of review all of the transformations. But a really important thing to understand is that anytime you're doing a horizontal transformation, that will be a change to x, whereas a vertical transformation will be a change to the function as a whole. So if we're multiplying by 1/3 outside of the absolute value bars, that means we can interpret this as a vertical stretch or compression. So what is it specifically going to be? It's going to be a vertical. Okay, so is it a stretch or a compression? Well, remember that vertical stretches and compressions work basically the way you would expect them to. So if the number you're multiplying by is less than 1, it's going to compress it. So it's going to be a vertical compression by 1/3. And so what does that mean? That means that we want to take all of our y coordinates on this original graph and just multiply them by 1/3 while leaving the x coordinates the same. So for example, the points that used to be at a height of 1 should now be at a height of 1/3. So I'll try to estimate where that would be. And I'm not going to do all of these. Let's do 3 because that's an easy one, right? So the points that were originally at a height of 3, well, what's 1/3 of 3? It's 1. So the points that used to be at a height of 3 should now be at a height of 1. And so once we have those 2 points, we can actually just connect them and use that to sketch our graph. So we can see that this has been vertically smushed downward, right? It's been compressed vertically. You might be thinking, couldn't you also see this as a horizontal stretch? And that would be correct. I don't really want to dwell on this because it's just not super important in this class at least. But if you wanted to, you could rewrite. So with absolute values, you can actually pull that number inside. So if you wanted to, you could rewrite this as absolute value of 1/3 x. And so then instead of seeing it as a vertical compression by 1/3, you could see it as a horizontal stretch by 3. So if you don't quite follow that, it's totally fine. I just wanted to quickly mention it in case you're curious. Like I said, because of the types of functions we're using in this class, there's going to be a lot of cases where you can see something in the graph as either being a horizontal or vertical transformation. I would just interpret it whatever is kind of the easiest way for you. So if you're given the function with a multiplication outside of the function, that should tell you vertical compression or stretch. Okay, so that is our first example. Let's look at another one. So in this case, we're going to use transformations to sketch or to graph. H of x is equal to the square root of 1/3 times x. Okay, so first thing, let's figure out what our original basic graph is that we're transforming here. So in this case, it's going to be f of x is equal to square root of x, right? And so I'm just going to go ahead and sketch that graph. Hopefully by this point, you're pretty familiar with the points on this graph. Okay, so that is our original function that we're transforming. So this time, we're multiplying by a third, but we're multiplying by a third inside the function. We're doing it to x, not to the function as a whole. And so that means that we want to interpret this as a horizontal stretch or compression. Let me rewrite it down here so that I can write on it better. So we want to interpret this as this multiplication by a third as a horizontal stretch or compression. So which one is it going to be? Well, remember that when you are dealing with horizontal stretches and compressions, you want to take the reciprocal of the number. So what's the reciprocal of 1/3? It would be 3. And so that tells us that it's actually a horizontal stretch by 3. So whatever the reciprocal is of that number you're multiplying x by, that just tells you what's going on. So if you get a bigger number, that tells you it's going to stretch horizontally. If you get a smaller number, that tells you it's going to compress horizontally. So what this means is we want to take all of our x coordinates and multiply them by 3 while leaving the y coordinates the same. So the point that was originally at 0 is going to stay at 0 because multiplying by 3 is not going to change that. But the point that was originally at 1, 1 is now going to be at 3, 1. The point that was originally at 4, 2 is now going to be at 12, 2. And that's actually the last point we're going to be able to fit on our graph. So what happened again is that, going through point by point, just to compare again. So here was like a point on the original graph. We multiplied it by 3 to get a point on the new graph. Oops. And then another point on the original graph used to be at an x coordinate of 4. We multiplied it by 3 to get the point on the new graph. And then we would also have a point with an x coordinate of 27, but that just doesn't fit on our graph here. Okay, so let's now do a couple of examples using our old friend here, this funky graph. So we're going to call this function f of x. And we're going to basically sketch a few different transformations of this graph. So first one that we're going to do is just 2 times f of x. Okay, so first question is, what type of transformation is this going to be? Well, we're multiplying by 2, and we're multiplying to the function, not to the input. And so that tells us that it's going to be a vertical stretch or compression. So which one is it going to be? Well, vertical stretches and compressions work the way that they seem like they should. So multiplying by 2 is just going to stretch the graph vertically by a factor of 2. So how are we going to actually make that play out in our graph? Well, again, if we just kind of select a few key points here, what we're going to do is just multiply all the y coordinates by 2 while leaving the x coordinates the same. So for example, the point all the way to the left, the y coordinate is currently -1. We're going to bring it to -2. The point that is next has a y coordinate of 1. That's going to get multiplied by 2 and be 2. The point that was originally a y coordinate of -3, multiply that by 2 and you get -6. This next point originally had a y coordinate of 1, multiply that by 2 and we get 2. And same thing with the next point. And then the last point on the graph is originally a y coordinate of 3, multiply that by 2 and we get 6. And so now we can connect our points and remember that we have this kind of curve shape in this middle portion. And so that is our graph. And so I just want to point out, I think I like to start with examples like the ones we did earlier in the video, just because, I don't know, it kind of allows you to see a little bit more what's going on with the formula. But I think in terms of really understanding what vertical stretches and horizontal stretches and compressions look like, I think using this type of graph actually is a little better for understanding what they actually look like in the graph. Because like I said in the earlier examples, there's a little confusion about, you can interpret the picture as either being a horizontal or vertical stretch or compression. But this one, I think it's pretty clear that it's only a vertical change, right? All of the horizontal stuff stayed the same. It still kind of starts here and ends here. So the domain is actually the same as the original function. And all that has changed is that it's gotten pulled upward and downward. So that's what a vertical stretch will look like. So again, all we did was just multiplied all the y coordinates by 2. Okay, so next one we're going to do is we're going to graph f of 1/2 x. Okay, so what is this transformation going to be? Well, now we're multiplying the input, and so that tells us it's going to be some kind of a horizontal change. And remember, we want to take the reciprocal, so the reciprocal of 1/2 is 2, and so that tells us this is actually a vertical stretch, horizontal stretch by 2. And so what's that going to look like in the graph? Well, it's going to mean taking all of the x coordinates and multiplying them by 2 while leaving the y coordinates the same. So for example, starting at the first point, the x coordinate is currently -1. Let's make it -2. This next point, and actually I'll mark these down again so you know which points I'm talking about. So the next point has an x coordinate of 0. When you multiply 0 by 2, it's still 0. So this point is actually going to stay right where it is. Next point originally had an x coordinate of 2. We're going to double that, and that will give us an x coordinate of 4. This next point originally had an x coordinate of 4. Multiply that by 2, and we get an x coordinate of 8. Next point originally had an x coordinate of 6. We double that, and we get 12. And then the last point originally had an x coordinate of 8. We double that, and we get 16. So now I'm going to connect the dots. And again, I think this might help you really understand, like, what does a horizontal stretch look like versus a vertical stretch, right? Because vertically, like, this graph still takes up the same amount of space. Nothing really changed vertically, but we can see that it got pulled to each side horizontally. The numbers that were already negative became more negative. The numbers that were already positive became more positive. All right, so that is it for this video. Please check out the worksheet for today. And as I said, in the next video, we'll do a complete overview of all the different types of transformations. And we'll also talk about how to apply multiple transformations to one function. So I'll see you all in the next video.